All right, thank you. I'm very happy to be here and with our friend Annie, the Enigma, who I've bonded with. But anyway, so I wanted to talk, in my mind, modern cryptography begins with the Enigma. And the reason for that, and specifically it begins in about 1930. So the Enigma was designed after World War I because by a German engineer named Arthur Scherbius. And the motivation for designing the Enigma was that time after time, these substitution cipher-based algorithms were failing, that they kept getting broken. So this was designed to be unbreakable, and the first part of the talk, I want to go through the historical steps which led to this design and led to the mindset of why it should be unbreakable. At the same time, in early 1930s, Poland, actually confronted with this device, decided to hire mathematicians. So before 1930, to my knowledge, mathematicians were not as much involved in cryptography. I guess there is definitely an exception because we did have Yardley before that. But this was a time where mathematics really played a major role in wartime cryptologic. And so this is where I'm going to begin with modern mathematics in cryptography. Okay, so we'll start with kind of what ideas led up to the design of the Enigma machine. So first of all, we had the Caesar cipher, which you've probably heard of. It was just shift everything by 3. Well, Z goes to A, B, C, right? Okay, and if you identify A equals 0, B equals 1, Z equals 25, then the Caesar cipher of I is I plus 3 mod 26. And you could shift by any amount. So this would be C sub 3, where I'm identifying D with 3. Okay, so D equals 3. The 3 just tells where does A go, right? And then C3 inverse, which is the decryption, is just going to be C 26 minus 3, which is the same as C23. Okay. This is clearly not a very sophisticated cipher, but it worked at the time, and you do have to consider that at the time people would see the encrypted thing and they didn't know the method being used. When you get into more sophisticated sophisticated wartime efforts, you have to assume that the cipher method is known because at some point during the war something gets compromised, and so later cryptography was designed with the knowledge that maybe it's known. So something more secure than the Caesar cipher is just monoalphabetic substitution. So this has 26 possibilities. And this has 26 factorial possibilities. Okay. This is a lot harder, and it was secure for hundreds of years until in about 800 AD, the Arabs discovered it was subject to frequency analysis. So what's the most common letter in English? E. So you look for the most common cipher, and you think, well, maybe that's an E. And if it's not an E, then maybe it's another common letter. So the most common letters are E, T, N, O, R, I, A, S. And you can also look for patterns between diphthongs, repeated letters, and so forth. So that one is also not secure. And there's quite a bit of colorful history about monoalphabetic substitution being broken and causing executions and all kinds of colorful history about that. All right, so we go on to the Nearsighted Cipher. By the way, I should disqualify myself. I'm not really a historian. It's just I've read a little bit, so please don't take my history too literally. That's not my training. But I wanted to just give some perspective on the ideas that led to the enigma as best I can. So what this is interleaving several Caesar ciphers. Okay, so you shift by 3, then the next letter you shift by 7, then the next letter you shift by 14, and so on. And then maybe after some time you repeat. So it has some period. Okay, so this was actually secure, I've heard, for 300 years until an attack was found against this system. And the attack that was found is sometimes you have common patterns, T-I-O-N, MENT, common patterns. And if it happens that fragment of a word is repeated at the correct offset that matches with the period, you'll see the repeated ciphertext. So these things can cause repeated ciphers. And so when you see such repeats of 3 or 4 letters in a row, you suspect, oh, I bet the length between the repeats might be a multiple of the period. So you get a few of those, you take the greatest common denominators of the offsets, and that tells you the period. Once you know the period, then you can do multiple frequency analyses. And one on each, one for each cut of the period, and solve that way. Question?
You need a rather large sample, right?
You might need a longer message, but in any case, it's better than Caesar cipher by itself, but it's still not secure. And for that matter, monoalphabetic substitution needs a fairly large. You have trouble doing short messages with frequency analysis. The longer the message, the easier it is to break for these systems. So now imagine, I should mention one other cipher which was used during World War I, and I will never remember the name of it unless I look at it. So this is called the ADF, very strange name, ADF GVX cipher. And this is this is not encrypted. This is plain text. It was used during World War I in Germany and by Germans, and it was broken by the French. So what they did, the reason for this choice of 6 letters is they have very easily distinguishable Morse code patterns. So what they did was they simply made a 36 by 36 grid labeled by those letters on each side. They put the plain text letters inside. So, put your A, B. You might want to put, since E is common, let's put it a couple of times, E and maybe somewhere else, E, and so on. And you fill out this 36. You even have a little room for punctuation. This is luxurious. So you fill out the 6x6 grid, and then when you want to encrypt your message, you just give the coordinates. So if I'm sending a letter C, then I just do DG. And then I just keep sending pairs like that. So this was broken by somebody who used to, I think his name was Penan. Sorry if I got that wrong. Oh, yes, by Captain George Pinvin. Oh, bread and wine. And he had been a geology teacher and then was recruited into the Bureau de Chiffres in France. So smart guy, and he found an attack which worked when the beginning and the end of several messages could be cribbed. And so this was unbeknownst to the Germans, but after World War I ended, this information came out, and so there was great motivation to build something better than all these things. So up until this point, cryptographers, for the most part, and I'm sure I'm wrong, but for the most part had been trained in linguistics, the classics. They were people who were very, very good with languages, and that was their primary skill. But now we have Arthur Scherbius, was a German engineer, and he designed the Enigma in the 1920s. Oh, I'm sorry. I left out one other code I meant to mention. If you can imagine Nearsighted cipher that never repeats. That would be what you call a one-time pad. Okay. That would, if a one-time pad, random sequence of numbers, and you just do this addition mod 26 onto your plain text message, that's completely secure. I think most people, everyone should agree, that is secure. And so this is one ideal goal that Scherbius might have had in mind when he's designing his cipher, if it never repeated. Okay, and another thing to say is that if you use a one-time pad more than once, that's bad to do, because what can happen is you could, if you make a guess, maybe you think those 4 letters are MENT on one message, then you can figure out what's the one-time pad, and then what would that look like on the other message. And if it starts to look like English, you say, okay. So the one-time pad, there's a real emphasis on one. Better just use it once. So all these principles were understood by Scherbius. Okay. So what he did was he made an electromechanical device this one, and it's based on you have a key. When you press the key, it does two things. The first thing it does is it completes a circuit, and the second thing it does is mechanically adjusts the permutation. So press a key, and that completes a circuit. And where does the circuit go? Okay. where does it go? It first goes, so here's the key. It first goes through a plug board, and that's a bunch of swaps of the letters. Okay, it'll just do swaps of some of the letters, maybe not all of them, or definitely not all of them. But it'll swap initially 6 pairs. Later it was increased to 10 pairs of letters. So when you press the key, it completes the circuit. The circuit, let's suppose if this was an A, it would first come here and it would come out a B. So it would be as though you had typed a B. After that, it goes through, this is the main part of the machine. You have these rotors, which imagine these being like hockey pucks. Each rotor has connections on both sides. These are spring connections, which actually, I didn't draw it that way, but they actually will touch the next rotor physically. And then on the bottom you have sort of just dot connections. So the spring connection pushes into the dots. And so these are wired together, but inside of each rotor, the rotors are labeled 1, 2, or 3. They can be put in any order, and each rotor has its own unique wiring. Okay, so if I type in, the B comes in, and it just enters into the first rotor. It gets rewired through. Then it goes into the second rotor, and its internal wiring of the rotor takes it somewhere else. And then finally, it goes into the third rotor. It gets sent somewhere else. And then up at the top, you have this reflector. And the reflector just has order 2, okay? Upon which it comes back through the machine the same way as though you'd started. Just kind of comes back following the wiring. And then it goes all the way back, even through the plug board again. And then finally, it lights up a key. This is a light. And so when you type in an A, you get a D, because it just traces through the circuit. Now notice if you typed a D, you would just follow the exact path that I drew backwards, so you'd get an A. Okay, so encryption equals decryption. That's an important feature, and that's for practical matter. You have to, if you had a machine that does a wonderful unbreakable encryption, but the intended recipient also has no idea how to decrypt, that wouldn't be a good idea. So this is a nice feature. Another point about it is that nothing encrypts to itself, because this reflector has no fixed points. Okay? All right. So that's the basic idea how the machine works. Why did they think it was unbreakable? Oh, I didn't say when the other physical thing that happens, so this is the electrical aspect of the machine. It's also mechanical. The mechanical aspect is when you push the key, there's a lever underneath with notches attached, and it causes the bottom wheel to rotate 1/26th around. So it rotates by 1 letter. Every time this wheel rotates, it's equivalent to conjugating this permutation by a Caesar cipher shifted by 1. As a result, you get a new substitution, new encryption with every keystroke. Question?
Yeah, okay. I'm sure somebody explained this yesterday. But so you have the plug board, and then you have these things that you slide in. And it seems like they both give you permutations. Why not just have the plug board and have an extra circular thing? I think I'm missing something.
The plug board was really added as a way to increase the size of the key space. So it protects against exhausting across all possible rotors, rotor positions, etc. So I think that mainly it's done in a simple manner. Mathematically, there's no reason it couldn't be like another rotor with a fixed permutation or something. But the thing about the plug board is if it was a fixed permutation, as soon as that permutation is learned by the adversary, then it wouldn't provide any additional security. Whereas the plug board, you can see it right here, it's something the operator can work into the cryptovariable. They simply decide, well, I'm going to connect R to a T, and I'm going to connect, so those work into the cryptovariable, and okay, later. And so if it was just a fixed wiring, even though it was better mathematically, but it would be known eventually and wouldn't add to the security. This one, you can add it into the crypto.
Can I ask about the reflector? Is that fixed? Is that permutation fixed? Or can that
Yes, the reflector, this is reflector B in this particular machine, but that would be, they would not change out the reflector. They would only change out the rotors. So the cryptovariable consisted of, so which rotors to use. Initially, in the 1920s and early 1930s, there were only 3 rotors. But then over time, they increased to 5 rotors, and at some point, even 8 rotors. And each rotor has a Roman numeral labeling it. You'd have to remove it to see the Roman numeral. So part of the cryptovariable is select the rotor. So let's look at the particular, I have the Wehrmacht Enigma with me. You would select one of 5 rotors, and you could choose where to put it, and then choose one of the 4 remaining, choose where to put it, and one of the 3 remaining, choose where to put it. So that would be 5 times 4 times 3 is 60 possibilities of where to put the rotors, how to order the rotors. In addition, you can select the number showing on the top the rotation of the rotors. There's a little window which shows you the setting of the rotors. So you could choose the setting. So we've got 5 times 4 times 3, and then you have 3 settings. It's 26 cubed. They wanted to make that number bigger. So by adding in the plug boards, when you add in 6 plug boards, you get something like 100 billion permutations, I believe. So that provides a huge, this is just from 6 plugs. That provides a combinatorial explosion of the number of possible keys. Mm-hmm.
So like when you open it up, you can see which numbers or which letters are switched on the plug board. So how does that like add security? Because if they intercept it, they can just see which letters.
Ah, okay, because they have some physical security on the machine. So you're right, though, that let's suppose that a U-boat gets compromised. What they would normally do is throw everything overboard. But it could happen that they found the Enigma itself. From that, they could, number 1, learn the wirings if they don't already know them. And number 2, they would see that day's settings of the plug board. And but those didn't happen all the time. It did happen. It was a very important aspect of World War II was especially they would go after weather ships and find the weather ships were kind of way out north, and sorry for all you Canadians, I'm sorry. they were a little bit like, kind of, it was easier to attack a weather ship, and they got a lot of information that way. Uh-huh.
So how are the plug board settings determined? Like you said that each operator would be able to choose which one, but like how would, like is it that individual operators have their own settings, and then you
That's a great question. So the question is, how do you determine what the key is so that both parties know what key to use? And one particular method which was used by the entire military at least through 1938, and then it continued to be used by part of the German military. So this is the method, how do you set the keys so that people can communicate with each other. So there were daily settings which were distributed physically as a booklet. And you would get a couple of months at a time of keys. So if somebody's daily setting keys were stolen, the enemy would be able to read for those 2 months until they were redistributed. So the daily settings contained, what were the plug board? Which was called also Stecker, that was the German word. The plug board settings, the choice of rotors and the ordering. And also the initial setting of the rotors. So with this information, everyone kind of has access to the same one-time pad, more or less. If you all set your machine the same way, you are reading the same, you're encrypting with the same permutations. All right. As I mentioned earlier, it's a sin to reuse a one-time pad. So what do they do instead? Okay, instead of, what they do is each operator selects their own 3-letter code corresponding to the initial setting. So this is the 3 letters. Which they'll use for their messages, to be used for their messages. So for example, maybe they choose WAM. Okay. Then what they do is they encrypt it twice using the daily settings. Okay, now they have an actual message attack, and this they encrypt with same settings, same plug board and rotors, because those would be time consuming to move around. So you just leave those the same, but the rotors, set rotor positions to WAM. Okay. Now the recipient, so this gets encrypted to something, like, I'm just making this up. Okay. So it gets encrypted to something, and then the message also gets encrypted to something. Okay, so the recipient, they first decrypt this part with daily key, and you remember encryption is the same as decryption. So they set the daily key, they type in a B, type in a G, type in an L, VIP, and out comes WAM, WAM, and they say, yes, it repeated. And why do it twice? Well, that's because maybe there's some garbles in transmission, so it's better to do it twice, and then they can make sure they got it right. They get a check. And then now they set rotors to WAM, and they start decrypting the whole message. Okay? So then they can see attack, get the whole message back. And what this does is you don't see any depth between, there's no reusage of the key. So that's how they protected against using the key twice. Okay? Any questions? How that works?
With the plug board, did they have to come up with 6 pairs, or could they have?
That was inside of the daily key, so yes, they had to use it.
So they had to use 6.
Yeah. Mm-hmm. It was 6 pairs later, it was 10 pairs. All these numbers kept changing throughout. And also at some point during the war, they even created a new upgrade using 4 rotors. So everything kept getting harder as the war went on, and there were periods where the Allies were reading the Enigma and other periods where they couldn't read the Enigma, and you could trace the history of how many ships were sunk. And anyway, I should say also this has a lot of personal significance to me because my father and his siblings are from England, and they were sent to the United States by ship across the Atlantic during World War II, and they came back. They came back separately. Actually, my father and his was second youngest, and he and his youngest were together. But they all came back separately to maybe make it more likely that at least one would arrive safely. They actually all arrived safely, and so that was my happy story. That I'm very thankful for all the code breakers. I'm sure many people are who broke the Enigma and made it a little safer to cross the Atlantic during World War II. Okay. All right. So now I want to give a little background on permutations. So I think first of all, notation, you have a choice between left to right or right to left notation. And so let's say I'm going to be talking about permutations of the alphabet. But you could write sigma of x, and then if you compose that with tau, it would look like this. So if you do sigma first and then tau, it's written right to left, sigma tau. And the other choice is if you put the x on the other side. Now if I do sigma and follow that by tau, it's written left to right, sigma tau. And this is the choice that I'm going to use because I like it. Okay. And now there's a way to convert into cycle notation. Have you all seen how to convert permutation into cycle notation? Maybe I'll do one quick example. So cycles. Let's just take a quick example. A to C, B to E, C to D, D to F, E to A, and F. Okay, F going to what's left over, B. So then cycle notation would be A goes to C, C goes to D, D goes to E. Oh, I made a mistake. C goes to D. Oh,
D goes to E. So you need
A goes to C.
E to F.
You're saying they're going to E right now.
Oh, I see. I have too many.
Too many E's, because E is so common.
Yeah. And I have the opposite problem. Since E is a very common letter in plain text, when I write a random ciphertext, I have to force myself to occasionally put an E in there. And I keep on putting in too many X's and Z's. So I have this reverse bias towards, okay, so D goes to F, F goes to B, B goes to E. And so this is one cycle. But in general, you could have, this could have been a 3, 2, 1. And then the cycle structure is where you just, that's just the lengths of all the cycles. So in this case, it's just 1, length 6. That's it. Okay. Let's see. I can get rid of that. So I need a couple of results about permutations. So one, so sigma and tau are permutations. So one is that tau inverse sigma tau and sigma have the same cycle structure. And proof is just one line, and that is x sigma equals y if and only if x tau, tau inverse sigma tau, equals y tau. So in other words, it's like renaming. If you rename x to x tau and y to y tau, it's essentially the same permutation. So like if x1 xk is a cycle of sigma, then apply tau across the board. X1 tau, xk tau is a cycle of tau inverse sigma tau. Okay, so that's why they have the same cycle structure, right? Okay, now encryption has a special cycle structure. Remember that E equals its own inverse, and nothing is fixed. So that means that its cycle structure is, and anybody, what would be the cycle structure of something like this? Like if A goes to D, then D goes to A. It's all transpositions. B can't go to itself. It has to go to G or something. So its cycle structure is all twos across the board. And the same will be true if you conjugate it, right? Okay. This I'm going to call a pure involution. So the second result is kind of interesting. It's about the composition of two. This is due to Rajewski, Marian Rajewski. He was a Polish cryptographer who figured out how to break the Enigma up to at least 1938 based on some special properties of permutations. So here was the main theorem that he used and that he found and used. And you can read about it in his own words in his paper, which is attached to, you'll find it online. There's a link. Okay, so the theorem of Rajewski is, let's see, if sigma tau are pure involutions, then the composition sigma tau has an even number of cycles of each length. So has the property that each cycle length occurs an even number of times. Okay, it's not obvious. So examples, if you're talking about 26 letters, which we are, examples of legit would be 1313. Or let's see, if we did 2 6s, we could then do 2 3s. That makes 18. And we have 6 left over, so we could do it like that. I think that would be legal, I believe, if I had it right. 6 and 3 and 2 and 1 is. I did add right. Okay, so these are examples of the type. Okay, now the proof requires colored chalk. So, and I'm. Oh, did I get it wrong? 9, 11, 12. Oh, okay, let's just do 2 more ones. Okay. So here's the way the proof goes. Let's just do an example. I'm going to do sigma in red, and let's say sigma takes A to E, B to C, D to J, F to I, and G to H. And that's enough for the chalkboard. Won't go down to Z. And now let's say that tau takes A to J, B to F, C, D, E, H, I, G. Okay? So now let's look at sigma tau. And maybe I will move over there. Okay. So let me repeat over here. So sigma A, E, B, C, D, J, F, I, G, H. And tau, I had AJ, BF, CD, EH, IG. So now if you look at sigma and then tau, what are we doing? We're taking A to E, and then E goes to H, right? So the composition takes A to H. Next, what comes next? Do another sigma and another tau. So H goes under sigma to G. And so I'm kind of treating these like dominoes. Okay, and then G goes to I. And now I goes to F. F goes to B. And then B to C. What is the long cycle? And now C to D. Oops, yellow. Okay. And then this is where the composition's going. Okay. And then finally, D goes, are we there yet? D goes to J. And J goes, I think we might be there. J goes back to A. Okay. All right, so there we go. Now, you'll notice that we used up the letters E, the letters G, and the letters F, and the letters C, and the letters J. Those are all hidden on both, they've been matched up. So they're not going to occur anywhere else in the dominoes. They've already been matched up. Now what happens if we take the last domino and put it at the end, so if we move the AE over here and match it, so we kind of take this out and now do sigma tau going right to left. What'll happen, E goes to J. We're going to start picking out, let me put it up on top. So I'm matching the dominoes A with A now. Now the numbers which used to be part of the cycle, so the first cycle we did was A to H to I to B, D, A, back to A, okay? And the hidden numbers were the ones where the dominoes meet, E, G, F, C, and J. So what happens if we take the first cycle, put it on the end, and run backwards, right? So what happens? E goes to, now the A's are matching, so they're hidden. E is going to J. Oops, E goes to J, J goes to, so there's a role reversal. The ones that used to be hidden are now showing. The ones that used to be showing are now hidden. So what we get is E to J to C to F to G to back to E. And as you can see, they match up. We get 2 5 cycles. And there could have been more dominoes here, but the fact is that these letters have been exhausted on both dominoes, both sets of dominoes. So this is how they match up. They match up, one going in one direction, the other going in the other direction. And there's even a converse to Rajewski's theorem. You can see it in his paper, where if you, the converse is true if you have an even number of cycles of each length, then you can write it as a product of 2 pure involutions. And the basic method is you take a pair that are equal to each other and you set them up in this way so that one goes forwards and one goes backwards. So you have some choice on the rotation, but that's the idea. And that was the main tool that that he used to break the enigma. So now, how does that apply to us? Well, remember we have this example where WAM, and we encrypt it and we get BGL, VIP, right? So and each encryption is a pure involution, but they're different at each time. So this is at the initial setting, and then at each time you encrypt, you get a different substitution cipher. Okay, and then we get BGL VIP. Whoops, BGL VIP. What he noticed is that, look at this, taking B to V. Well, pi1 is equal to its own inverse, right? So I could go pi1 B going to W, and then W is equal to itself. Pi 4 going back to V. So V is equal to, let's see, if I take B and apply pi 1 and then apply pi 4, I get V. And this is cipher, so the attacker gets to see it. So there you go, B going to V. Through the fact that they are re-encrypting the same letter, and the fact that encryption equals decryption is what gets you there. So let me go through it one more time. So if you do B dot pi 1, you would get W. Then apply pi 4, and you get V. So we don't really care that this was a W, just knowing that they're equal to each other is what makes this work. All right, so we've collected a message, and from that we can see that pi 1, pi 4 takes B to V, and pi 2, pi 5 takes G to I, and pi 3, pi 6 takes L to P. All right, so you collect all day because there's lots of operators sending lots of messages, and so for that day you start getting enough information to completely construct these 3 special permutations. So you collect for the whole day. After you've seen maybe 60 messages or 90 messages or enough, you can reconstruct pi 1, pi 4, pi 2, pi 5, and pi 3, pi 6 for the daily settings. So for right now, we're just ignoring the messages. Mm-hmm.
For people that were like intercepting this message, how did they know that that was going to be like a length 3 repeated?
They know it because of kind of following the development over time. So the polls were earliest in the game, and they followed the commercial version, and there was simultaneously a military version. And then the military, it was really not too big a secret how they encrypted because they were, they trained a lot of people on it. There was also a lot more to the story, which I have left out. There was, in addition, a spy, a German spy, who gave information to the French, who then passed it on to the Poles, Hans Thilo, and they got the wirings, and they found some things through espionage.
Okay, yeah, because that seems like a big, like it seems like that should have been kept secret, you know?
Yeah, but sometimes, if the security of your machine relies on keeping everything secret, that's not good enough security because of the widespread usage.
Yeah, right,
okay. Okay. So there you go. You reconstruct these 3 permutations. What do you do with them? Well, let's find their cycle structures. And I will tell you in a minute why you want to do that. So your cycle structure, he called those characteristics. So you might have, like, the first cycle structure might be, well, the ones I wrote down earlier. Maybe one of them is 1313, and another one, the second one, might be 1313, and then the next one might be 10, 10, 2, 2, 1, 1, and so on. So you write that down. what it turns out is that these cycle structures are independent of the plug board. And that's a big deal because the plug board was what gives you the combinatorial explosion in the number of possible keys. So claim the cycle structures are independent of plug board. Okay, and let's just prove that. Okay, so let's say pi 1 is equal to the plug board times some permutation composed with the plug board. So rho 1 is just the permutation without, as though the plug board were set trivially. Okay, and the plug board is equal to its own inverse because it's just those wires hooking one letter to another. Okay, pi 4 is equal to the same plug board and a different row because the rotors have moved times, again, conjugated by the plug board. And remember, p equals p inverse. So now if you look at pi 1, pi 4, you get p rho 1, p, and pi 4, p rho 4, p. So the p's cancel, and here I'm allowed to write, since p equals p inverse, I can change one of them to an inverse. And there we have it. It's p inverse, rho 1, rho 4, p. You remember, conjugating does not change the cycle structure. Effectively, what the plug board is doing, it's like renaming the members of the cycle. So if you had some sequence of letters, L1, L2, LK is a cycle on rho 1, rho 4, then apply the plug board to each. L1P, L2P, LKP is a cycle on pi 1, pi 4. So really, you're really fortunate that P does, you can pre-compute the characteristics for, just make a table lookup of the characteristics only for 26 cubed times 60 possibilities, and the plug board does not factor in. So that's how Rayuski's attack worked. All right. Any questions on that? Yeah.
How do they actually go about finding the cycle structures? Because if you just have a bunch of like letters written down and you just have humans looking at that, it seems like it would be kind of hard to.
Oh, okay. So to find it was like this example. You have all the letters and you keep track of where they go, where they've been observed.
But like, were they actually just humans looking at it, or
Yeah.
was there? No.
Yeah. So humans would collect all these 6-digit ciphers, the initial 6 digits, and they would have a table of A through Z, and whenever a new message would come up, they would say, "Oh, okay, I just saw A, X, Y, C, something, something, so I know A goes to C," and they keep doing that all day long until they're able to reconstruct the cycles. Yeah. Uh-huh. Oh.
Sorry, if they only were able to figure out the daylight savings after the day, then then the daylight savings shift the next day.
Yes, they shift the next day, and so from the point of view of the Allies, it was better if they could decrypt on the same day.
So they could so they could read the messages that were read the day before rather than to know what was.
So let's suppose only at midnight you finally have collected enough messages that you can compute the signature, then you're going to be reading old news the next day.
Yeah.
Which is better than nothing, but you'd rather know today what they're doing today. So there was pressure to have the decryption go fast enough, and I will say this method worked early on. It's not clear to me. I'm not sure if I understand all the history exactly right, but I believe the Navy was more difficult to decrypt, and that the bombs, you saw the imitation game last night, the bombs were designed on a different scheme where they didn't want to rely on the initial, the way that the message was sent, the message indicator was sent. They rather just cribbed messages. And there was a parallel effort in the United States in Dayton, Ohio, involving Joseph Detch was an engineer, an American engineer, and that was a huge effort. They needed to, they created, again, it was electromechanical device to break the Enigma, and in order to keep up with the daily traffic, they needed the rotor to go 3,000 RPM, which for that day was just a huge challenge. Why 3,000? Well, at that time they were using 4 rotors, so they had to go to 26 to the 4th rotor settings, and by doing it 3,000 RPM, this is a reasonable number of minutes to be able to. I think it took about 20 minutes to run through all the rotor settings, and so it was a challenge to keep up. It was a constant back and forth who was ahead in the game throughout the war, and I think I was lucky that my aunts and uncles and father crossed in good months. So, yeah. Okay, I want to say one other thing is that this observation means that you can actually start to set the plug board. When you've collected everything, what you're seeing in your Pi 1, Pi 4 is L1, L2 with the plug board attached. Okay, you're seeing something similar for Pi 2, Pi 5, and for Pi 3, Pi 6 using the same plug board, and that turns out to be enough information to figure out what the plug board is. So if you're interested in learning about that, it's very nicely explained in my colleague's slide. His slides are available on the website. So, okay. Yeah.
Oh, sorry. This is going back a little bit. Did Rajewski understand the mechanics of how the Enigma machine worked in each of the parts, or was he just working without knowing that?
He did know the mechanics. He, in fact, initially he was trying to work at learning the wirings just from cryptanalysis. But there was a spy that kind of helped them, gave them the wirings. But so he, in fact, had a complete understanding of the machine.
Okay.
When he worked on it. Not the entire time through, but once he did learn the wirings, then they were very successful. He had some ideas, and you can read his paper, because he had a lot of ideas in there of how to recover wirings if you didn't know them. So it's very interesting mathematics, and it's very cool the way group theory worked out. Group theory saved lives. So, yeah. Any other questions?
We should thank Toni.
Okay.